30-second delay. Good evening, ladies and gentlemen, and I bid you a very warm welcome on behalf of the Railway Civil Engineers Association. Tonight's event will be on large landslides, dealing with the impact of adverse and extreme weather events, presented by Claire Brint, Nick Dewell, and Ben Leng. And here is a reminder as well that next month on the 31st of March, we will be hosting an event on railway overhead electrification, presented by John Dolan, a seasoned industry professional. He will be presenting on the benefits of electrification, the cost and issues, and how these can be overcome. So please come if you would like to hear about how electrification can be made affordable and practical here in the UK. We have partnered with the Permanent Way Institution to promote events that are of interest to each other's members. So if you would like to see what is available for the PWI, please go on the pwi.org, look on the list of their events, and register and attend any that may be of interest to you. And here's a reminder as well that if any of you are not already members of the RCEA, that if you satisfy us as to your suitability for the role, you'll be very welcome to join us at any time during the year. Our membership fees have remained discounted for second year running. Now, before we start, I would like to remind you that you can pop your questions in the Q&A panel to your right, and that there will be a Q&A session at the end of the presentation. That would, and now let's begin.
Okay, am I? Yeah, I'm on, I think. Welcome everyone. Thanks for giving us the opportunity to talk about our big landslide at Morpeth. I'm going to do a bit of an introduction into what our team does in terms of asset management and how we deal with adverse and extreme weather events. And then Nick and Ben are going to talk about the specific site at Morpeth. So first of all, I'm an engineering geologist. I did my degree at Leeds and then started working in the railways, doing inspections and designs for railway embankments and cuttings. And I now lead the team in York, doing the same, managing the earthworks in Northeast and East Coast region. So Network Rail, we've split ourselves into 5 different regions. The Eastern region, which we're part of, is detailed on the right hand side there. So the 2 routes that my team look after are the North and East route in blue and the East Coast in red. But we've got very close links with our colleagues in the south areas, East Midlands and Anglia. So what are we for? Next slide, please. So what are we here for? So we're supposed to manage the earthworks assets as well as ground related hazards, so that we can run a safe, reliable and efficient railway. So that's kind of what our purpose is. If you go to the next slide, please. So our vision, we have a very grand vision. We want to fully understand the risks from our earthworks assets, from mining and any other ground related hazards. And we want to mitigate those risks using the best tools and resources. So that's kind of where we want to be. And how are we going to do that? So we want to predict, prevent and respond to failures. So predicting failures, we want to really understand where the failures might occur. We want really good asset knowledge and hazard knowledge. We want to prevent failures from not necessarily from happening, but from affecting safety or performance. And the kind of programs of work that we'll instigate will be things like maintenance regimes, assessment, ground investigations, kind of renewal work banks, monitoring, and so those are the kind of work banks that we manage. And then responding to failures, which is what we're kind of going to talk about tonight, is what do we do when failures do happen? Make sure that we as a team provide the kind of technical and practical support to the operational teams, we kind of want to minimise safety risk and performance impact. So next slide, please. So my team just wanted to give you a kind of an outline of who we are and what the different bits do. So in purple is my maintenance teams, one for each route, North and East and East Coast. So the North and East has a team of 3 because it's bigger, it's got more assets in the North and East route. Then in green is my renewals and enhancements team. So they look after the planned renewals work bank. So the larger schemes. And then I've got a compliance and a support team as well, who help us obviously manage understanding where we are in terms of compliance with standards, but also providing some level of assurance that what we're doing is the right stuff. And the support team are helping with kind of building tools and trying to kind of integrate how we manage the assets within the kind of wider railway system. So we've got in yellow is our team of examiners. Up to this past year, 12 months ago, the examinations were being carried out via Amy Rail, but we have now brought the examinations in-house. So it's a brand new team. They're only kind of going the last 6 months or so. So they're really bedding in at the moment, but I'm really excited about what value they're going to be able to add to the asset management process. So that's who we are. So if we go to the next page, please. Thanks. So I just wanted to show you a few of the things that my maintenance teams will end up getting calls about. We get a lot of there's a hole. It must be mining related, or it must be some problem. Quite often it's a disused drainage system. So that's the one on the left hand side. The next image it might be a bit unclear. You'll see there's kind of a dip and then a rise in the rails. That's due to settlement that occurred while there was a ground investigation happening in the field above the cutting slope. We strongly suspect that it's to do with mining, historic mining. So that's kind of the thing they can get called about. Then the next 2 images are a track fault that happened down at a site called Harlington, and the fence that's leaning over is actually at the bottom of that embankment. So again, that's the kind of thing that the maintenance teams will be called about on a kind of day-to-day basis. So if we go to the next slide, please. So during adverse weather, there's 2 things that our team do in preparation for when we know we've got lots of rain coming. We've got a list of sites that we consider to be at risk when they get very wet, and we call those our adverse weather sites. And we've got a tool on the Network Rail Weather Service platform, which gives us kind of a red, amber, yellow and green alert level as to how wet each of those sites is and how much rain is forecast. And as a team, we get email alerts each morning, and when one of those is red, or if it's orange as well, we'll look at it and we will send one of our contractors out to do things like clear ditches or culverts, check that everything looks okay. So they'll kind of do that beforehand. We might send them out afterwards as well. So that's kind of one thing again that the maintenance teams do. It's our day-to-day bread and butter kind of stuff. So the next slide, please. So this one is around convective rainfall. So when you get really, really heavy rainfall happening, and very localized, what we've introduced in the past 12 months maybe is using this convective analysis tool, or convective alerting tool. So we've identified route sections, so it might be 20 or 30 mile lengths of track, which have earthworks which we consider to be at risk. They may not be ones that would be normally at risk, but during very high rainfall events, these convective events, we're not sure where something might happen. So what's been introduced is the control centre. When these high risk operational route sections, if any of those has a forecast for one of these convective rainfall events, they'll put speed restrictions on until after the rainfall event has passed, and the trains have indicated, you know, the trains that have gone through the section have indicated that there's no issues. So that's one of the other things that we do around heavy rainfall. And next slide, please. So this is just an example of something that's kind of a bit over and above the kind of day-to-day stuff that might happen, where you get told that, you know, a rock has fallen in the set, or you've got a little bit of you know, water coming down a cutting slope. So this is where we've got a proper landslip happening. I think it did happen following quite heavy rain. You can see in the little sketch that the embankment has kind of dropped. The photograph above, you should be able to make the track fault out. This was on the East Coast Mainline, and I think the milepost there, for those of you who may be interested, I think it's 66 miles. Place is Connington Loop. So the maintenance teams, again, they lead the recovery alongside our deliverers, the contractor, the designer, and the operational teams, and anybody else who may be kind of part of the recovery. So and then the little sketch on the bottom right shows the very sketch form of the kind of repairs that we'll do. So this site, for example, I think the incident happened and we shut the loop in August, and it took us a couple of months to get it recovered. So that's the kind of, again, relatively normal kind of landslips that happen within an embankment or a cutting that was built for the railway. So the next slide, please. So we also, so large landslides, I'm using that term to denote like hillsides, basically, where you had landslips that would have happened whether or not the railway was there. So this one is at a site we called Unston. It happened in 2014, as indicated there, and hopefully my little sketch helps. So it's a big site that's about 100 meters from the red line near the track is where the line, the troughing route was being pushed up, and the track was being pushed up, which you can see in the photograph on the right hand side. So that's kind of the toe of the landslip, and then you had the back scar is about 5 meters, I think, if I remember rightly, the back scar. And when we looked into it, we found that there had been a historic failure there, and we had forgotten about it. It was in the files when we went digging for it, but we hadn't known about it at the time. So if you go to the next slide, you can see how we repaired it. So again, my little sketch there, you can see we've put in what we refer to as a shear key at the toe, and then at a few locations, I think there's 4 sets of shear keys going further up the slope with quite deep drains draining the hillside. So that's kind of, and that this particular incident happened after there had been it felt like months and months of rain, so the groundwater levels were really, really high, and that was why this previous landslip that had happened in the 70s and had stopped moving, and we hadn't been aware of it. With the really high rainfall and the high groundwater levels, it reactivated the landslip. So that's why it happened again in 2014. Okay, next slide, please. So this next one, when it comes up, so this is at a site at Galcar over near Slowett, or as I previously referred to it, Slaithwaite, and was laughed at. So at Slowett, so what we're looking at here is the top left-hand image. You may be able to make it. So there's a track, and the track actually dips down, and it had been dipped down like that for years and years. There had been no indication of movement. It did indicate that there was probably something going on. And then the ground, so you can see the railway boundary fence there, and then the ground falls down towards a canal, if I remember rightly. And in 2020, if everyone remembers the winter of 1920, just before a lockdown, it was very, very wet. There was lots and lots of flooding. And this was one of the incidents that happened in that early, I think, February 2020. And it was first reported. Now, in the top left-hand photo, you might be able to see some kind of white in between the trees. That is actually a Yorkshire water pipe, a high-pressure water pipe, like doing a fountain. And we think that actually cracked because the landslide was reactivated again because of the very high groundwater levels. So you can see in the bottom photograph, you can see there's kind of a crack in the path, and that is where the new movement was happening. So the top photo, where I've kind of put two images together, kind of gives you a sense that the railway is up on the top right hand side of it, and the canal will be down the bottom, kind of in the left hand bit, and that's the kind of size of the hillside you're talking about, where that was reactivated. So if you go to the next slide, please. So just to give you a sense of the kind of scale. So what happened at this site? I think there was an original, a historic landslide, which was, you know, a natural landslide. We built a railway on top of it, and you know, it hadn't been moving much more. But then I think there was a secondary slip that formed, and what we've done is we've put a series of piles through it. But again, the key thing about this particular site for this story is that it was very high groundwater levels that reactivated a historic slip. So the next slide is more. So now we're into Morpeth, and I'm going through this pretty quickly. So there's a history here. The line was constructed in the mid 1800s. They widened the embankment. They then filled the ground on the uphill side of it, and they blocked a culvert as far as we know. And that was the first time they started recording reports of track faults. We suspect a connection between the two, but the records aren't very clear on that. So they did do ground investigations. They did some monitoring, and they installed some drainage in the mid 80s. And then again, it kind of got lost in the midst of time. In the 2000s, we started identifying more track problems, and we carried out an assessment during the kind of early 2010s, I think. At that point, we thought the instability that was evident at track level was due to the rail embankment, which was failing due to poor drainage. So we installed a stone berm in 2015. It didn't fix the problem though. So the track problems persisted, and then the OLE started giving problems. We continued doing more monitoring and installed some inclinometers, and started recognizing that actually it was a much bigger slip than we had previously recognized. So at the moment, there's new OLE masts going in. Those should be all installed sometime in March. We've done some temporary works, which you'll hear all about shortly, and we're doing a big piling scheme. So that's kind of the essence of it. So if you go to the next slide. So this is just showing you the layout of it. It's just north of Morpeth, and you can see the EJM line comes off on the east side. Okay, you can go to the next slide, please. So I've got a series of cross sections here, and I'm not going to go into these in detail. I just want to, the reason I've got these, I want to show you our kind of thought process and what we knew. So we were reacting to this issue and like live attempting to help manage the track problems, but also attempting to understand what was going on and what was possible and what we needed to do to try and fix it. So at the time we knew it was a deep slip, but we didn't know whether the slip surface was coming out halfway down the slope or much further along. So if you go to the next slide. Oh, and you can see on these little cross sections as well, you can see the little yellow triangle where we installed the berm in 2016 that didn't solve the problem. The additional boreholes in the lower slope confirmed that the slip extended the full height of the hillside. The next slide, please. And then we discovered that there was actually a secondary slip, which is in the darker red line there that was actually affecting the embankment itself more than the hillside. Next slide, please. So this is, again, very sketch form, but the idea, we knew it was going to take more than 12 months to get the whole project done. So we thought we've got to do something to bring the water levels down and try and protect the railway during the winter months. So you'll hear more about this, I'm sure, from Nick now, but we installed some incline drains to pull the water down, and steel piles towards the toe of the slope. And then the next slide, and I think that's my last one. So this was, at the time, this was back, you know, a number of months ago, the concept was that it was likely to be maybe 3 rows of deep piles would be the permanent solution. That has changed now, but I'm sure Nick will guide us through the detail of that. I think you're up next, Nick.
Right. Thank you very much, Claire. Can you all hear me? Yeah, there I am. Right, thanks for that, Claire. I'm sort of on the next 20 minutes or so, hopefully not too much longer. Just going to look at the process that we've gone through as designers on the Morpeth scheme to investigate and monitor the landslide, and then the process that we followed to design the remedial works that Claire's just described, and as briefly as I can, just to sort of describe the design and the philosophy behind that design. So Pell Frischmann first became involved in the Morpeth scheme back in 2020 when Network Rail obviously issued us with a remit to send a geotechnical specialist to site to carry out a site inspection and look for signs of instability. That was instability of the ground that was causing all these track faults, and then to just develop a monitoring plan, just to measure that track movement and movement of the embankment side slope for a period, just to determine the causation. If you can have the next slide, please. So this is a series of photographs taken from our initial site inspection, and what we can see here is this is a view from the sort of mid part of the site, looking towards the high mileage, so towards the east, away from Morpeth, and that's taken from someone stood on the embankment crest, and you can see the embankment side slope in the foreground, which is a sort of browner grass, and then in the distance we can see the sort of natural concave topographic landform that the embankment's constructed on the side of, more or less meeting the crest of that natural landform. And then looking to the north, can I have the next slide, please? And this is again stood on the same position on the sort of down cess embankment shoulder, looking north, and again you can see the browner grass of the embankment side slope, not particularly steep, round about a 1 in 2 gradient, and then at the toe of the embankment you can see what we always refer to as the upper and lower hillside, which is the very hummocky ground with lots of breaks in slope, very characteristic of a sort of landslide topography. Then at the toe of the hillside, where we've got the hedgerow, we move into the arable farmland, which is essentially the river floodplain of the River Wansbeck, which I think is about 600 metres or so north of the site. And then if you can have the next slide, please. Again, photo from the same position, looking towards Morpeth. Again, you can sort of see the railway disappearing off and on the left hand side of the picture, and then again the sort of concave natural topography curving off to the right of the picture, and the embankment side slope eventually grading to nothing as the railway approaches Morpeth station. Next slide, please. These are a few of the photographs taken at track level during the initial site walkover, and this is just to show some of the features that showed some of the features of landslide sort of topography and some of the issues that we picked up. I mean, the first thing to note on this picture, in the distance you can see a line of fresh ballast where obviously the tracks have been tamped to try and recover some of the track failures, and you can almost follow the line of fresh ballast to the drop in the S&T trough, which kind of marks the sort of curvy linear nature of the landslide backscarp as it crosses over all four of the tracks, and then it actually goes into a container yard to the up side of the railway. So we can have the next slide, please. And again, what you'll notice there is on the sort of roof line of the containers, and again on the fence line, we can see a drop in the level of the containers and the boundary fence and the S&T trough, which all become lower inside the area of track deformation, and these are indicative of the change in level caused by the landslide. The landslide containers also showed evidence of lateral movement as they curved out towards the abscess in the where the drop in levels at its greatest, and that's all indicative of the landslide backscarp creating a drag on the line of containers. And also you can't see on the photograph, but at this end of the containers they're all chopped up on bricks, just to set them level as they sort of fall into the landslide backscarp. Can I have the next slide, please? And yeah, this is looking down to low mileage towards Morpeth, and you'll notice that I don't think I was stood at a jaunty angle when I took the picture, and that's actually the lean of the OLE stanchion, which again is leaning, sort of following the deflection of the backscarp and leaning down slope. And also again in the background you can see the line in the ballast where fresh ballast has been placed to correct the track faults. Can I have the next slide, please? So following the initial site inspection, we recommended setting up a monitoring system and further ground investigation on the site, because I think a lot of the existing ground investigation that was done for the design and construction of the granular berm in 2016 was fairly limited in depth. It just kind of really investigated the earthwork itself and the shallow ground beneath, and didn't really go deep enough and far enough onto the hillside to develop a very good sort of full ground model of the site. So we set up this monitoring system in late spring 2020 and monitored it throughout the summer. And I don't know if you remember at the beginning of lockdown, we had quite a glorious spring and summer, clear blue skies, so very little rain. So of course, this monitoring period didn't really record any significant ground movement, and everything seemed relatively stable throughout that period. Can I have the next slide, please? That kind of changed in winter 2020, winter 2020, when the track faults were all reported again. And around this sort of time, we started on the ground investigation, and say to sort of investigate the influence of the ground movement on the hillside and embankment. And we carried out the ground investigation by installing an awful lot of inclinometers across the site. We had rows of inclinometers in sort of 25 to 40 metre deep boreholes on downcess, another line of 25 metre deep boreholes along the embankment toe, a further one on the hillside, and then some shallow boreholes with inclinometers towards the toe of the hillside. We also installed extensometers in the 6 foot in the, I think that was in the downslope, just to check for any settlement of the embankment and the near surface soils, and also had piezometers in the container yard within 35-metre deep boreholes on the upside of the tracks, just to determine how groundwater levels behind and under the hillside might influence movement of the tracks. And as part of the ground investigation, we also carried out a geomorphological survey of the site to check for any indications of ground movement, such as tension cracks, backscarps, breaks in slope, and groundwater seepages and various other things. So the ground investigation actually started in January 2021, and that was round about the time that we had what Claire describes as one of the adverse weather events, and everything started to move quite significantly. You can go to the next slide, please. So this is a photograph towards the low mileage of the track faults that developed on all 4 lines in February 2021. As I say, these are sort of evident of the line of the failure backscarp, which curved across all 4 tracks into the container yard, and then back across all 4 lines towards the high mileage. If you go to the next slide, please. And this slide shows the there we go. This slide shows the findings of the geomorph survey, and what we've marked on there. I mean, you can see the sort of curvilinear line of the backscarp crossing the tracks, going into the container yard, and then back across all 4 tracks and down the hillside. But other than the actual track deformation and the container level and positioning, there was no actual evidence of the backscarp to the main landslide observed in the geomorph survey. What was more evident was the toe of the main landslide, which was interpreted as a very steep toe of the hillside and just above the arable field, with lots of seepages and, you know, quite clearly lots of disturbed ground. But as I said, quite surprisingly for a landslip of this sort of magnitude, that there were no clear tension cracks or shear surfaces actually observed at the surface during the survey, and probably a function of just how wet the hillside was at the time that such features were sort of masked. I mean, what the geomorph survey particularly picked out was a lot of hummocky topography on the upper hillside area near the toe of the embankment, which again is typical of landslide terrain and probably indicative of shallow slope failures within the larger landslide system. Across the remainder of the upper and lower hillside, the hummocky ground kind of became a bit more sporadic and smaller towards the toe of the landslide, which we, as I said earlier, sort of identified towards the base of the hillside. Green symbols on the plan there, they represent boggy ground and hydrophilic vegetation, which is generally coincidental with sort of relatively flat areas on the upper and lower hillside, and tends to also coincide with the geological boundaries, which again tie in with some of the steeper areas on the hillside where we think you know, various landslides are emerging at the hillside. If you can go to the next slide, please. This is the ground model that we developed from the site. It's shown in cross section and highlighting those geological boundaries. And this sort of pulls together all the information that we got from the ground investigation, the geomorphological survey, the monitoring of the piezometers in the container yard, and the looking at where we saw movement in the inclinometers installed throughout the site. Just to sort of go through the natural geology first, like a lot of sites in northeast of England, we tend to see a sort of tripartite system of glacial soils where we have a glacial till, sand, and then a laminated clay in sequence. And on the Morpeth site, we have an upper glacial till layer, which is shown in green, underlain by a sequence of a sand and silt deposit, and then a laminated clay, which is shown in blue, which in turn is underlain by a lower glacial till, which all sit on top of the bedrock, which is penine lower coal measures. Made ground across the site was just limited to the container yard and the embankment itself, and the made ground thickness in the container yard sort of increased from south to north, suggesting that the original ground level had been infilled at some time in the past within the container yard, just presumably just to level regrade the container yard when it came into use, and that infilled the sort of natural crest of the hillside right up to the crest of the railway embankment. Based on the where we'd seen movement within the inclinometers and where we'd seen evidence of the backscarps from the track faults in the geomorph survey, the primary landslide failure plane, the deeper one, was interpreted to sort of running cross section as a steep rotational failure below the container yard, into the embankment fill and through the sand and silt before the landslide sort of followed a more shallower gradient, becoming translational almost in the laminated clay above the boundary with a much stiffer lower glacial till. And obviously the main mechanism for this translational failure being the loading of the East Coast Mainline embankment on the head of the landslide. What was also evident from the borehole logs was that the laminated clay softened within this sort of translational shear zone, and on the borehole logs it was very evident in the end values from the standard penetration test that where we're in the laminated clay above the shear zone, the SPTs were generally single figures, ones, twos, even zeros. And then as soon as we got below the failure plane, they increased to 19s, 20s, and it was a very marked increase, which you could follow in all the boreholes moving down the hillside. And again, if you were to mark the areas on the inclinometers, sorry, the depths where we'd seen movement on the inclinometers on the borehole logs, this also tied in with where we saw this increase in SPT values. And going down to the toe of the slope, again, we saw a series of steep-sided hummocks with groundwater seepages, which again we sort of interpreted to most likely be formed by the toe of the primary landslide, which transitions subhorizontally through the laminated clay and emerges, as I say, at the toe of the hillside. We also have a secondary landslide, which is a lot more rotational, with the backscarp just limited to the downslope track. And we again picked this up on the track monitoring because we had a series of track faults just on the downslope track, which bisected the sort of curvilinear series of track faults that affected all four tracks. And in cross section, I mean, the secondary landslides inferred to be rotational and run steeply through the railway embankment fill and then transitions more subhorizontally through the upper glacial till. Daylights at ground level coinciding with a series of, as I described in the geomorph survey, a series of hummocky features on the upper hillside just at the embankment toe. Can I have the next slide, please? This is a sort of simplified sketch of the ground model. I think it's quite useful for when we're looking at the groundwater levels in the site. I mean, what we found in the ground investigation was that groundwater levels generally encountered about 48 metres above ordnance datum, particularly within the sand and silt level layer in the container yard to the upside of the railway embankment. At the time of the ground investigation, I think when we first put the boreholes down in the container yard, we were seeing much higher levels, around about 50 metres AOD, which we kind of weren't entirely sure whether that was due to introduction of a lot of water flush into the boreholes at the time, or simply reflective of a much higher groundwater table at the time of the investigation, which was shortly after this adverse weather event. And again, we've got a relatively high piezometric head of 48 metres above ordnance datum in the container yard, and that kind of explained the presence of numerous sort of springs and seepages and boggy areas that we described in the geomorph survey around the embankment toe, the embankment slope, and on the hillside itself. And we generally found that on all the drillers' logs for the boreholes excavated on the hillside, that groundwater was generally between half a metre and a metre below ground level. Also, sort of key to the groundwater is its influence on movement on the site, movement of the hillside and the embankment. We obviously looked at water levels in our slope stability assessments, and by back analysing the groundwater levels and their influence on the slope, we found that in the back analysis, when we had the groundwater level set at what we call a characteristic value of 48 metres ordnance datum, stability on the embankment and hillside was more or less around unity. But as soon as we increased that groundwater level up to a critical level of 50 metres above ordnance datum, that factor of safety dropped well below 1. And that again clearly shows the influence of groundwater and on movement of the hillside and the embankment itself. Can the next slide, please? And this slide shows the inclinometer monitoring results from the series of inclinometers that were installed from low to high mileage on the embankment crest. And the scale doesn't actually lend itself for a very good visual aid, but what you can see is that the depth of the slip surface is deepest in the centre of the site and shallows to the low and high mileage. So we've got 19 metres in the centre of the site, and then low mileage it's about 10.5 metres, high mileage it's about 16 metres. And again, that's kind of reflective of the concave nature of the natural hillside below the embankment, where we've got the greater embankment height in the centre of the site and reducing to the low and high mileage. And what we can also see from the inclinometer plots is how movement reduced significantly from what we were seeing in February, March 2021 of around about 1 millimetre a day or 7 mil a week. In that, following the adverse weather to when we got the much drier period through late spring and early summer, we were back to seeing less than 0.5 mil of movement a week. More or less just sort of a residual creep of the landslide rather than any sort of active movement. And it's round about this period where we're seeing little movement again that we began work on the design, and obviously we expected movement to increase again with the heavier prolonged rainfall events as we approach the end of the year and winter, well, 21-22 where we are now. So obviously this gave us a very short time frame to design, procure and construct a longer term remedial solution before significant movement resumed in winter 2021. So we proposed that we installed an interim, sort of quicker to install temporary fix in the meantime to sort of provide or to reduce the impact of any higher pore water pressures on landslide movement that we might see as we entered winter in 2021. Can I have the next slide, please? And again, just to note that, as I say, this was a short-term interim solution. It wasn't intended to provide long-term stability to Network Rail, Eurocodes or British standards. It was just there to improve stability such that the site would be better able to handle any increased rainfall events over this winter while we designed, procured and installed the permanent solution. So the interim solution itself comprised a series of 2 rows of sub-horizontal drill drains installed into the lower hillside and into the toe of the embankment, and into the sand and silt layer. The purpose being to try and keep that characteristic groundwater level round about 48 metres above ordnance datum, make sure it didn't creep up to 50, and which would be the point where we'd start seeing significant movement of the hillside and embankment again. And together with the sub-horizontal drains, we installed a staggered sheet pile wall to intersect the basal shear surface of the primary landslip. And to make sure we were getting the water off the site, we sort of proposed improvements and repairs to the existing slope drainage and establishment of an outfall for that drainage. The sheet pile length and most suitable location for the sheet piles was kind of dictated by the need to provide a design that could be, as I said, constructed quickly and using off-the-shelf materials. And obviously Story got on the phone and found out what was available, and we were, I think that the ready off-the-shelf material was a 12-metre long sheet pile. So sort of together with the topography and geometry of the basal shear surface of the landslide, controlled where we'd be able to place the sheet piles such that we get sufficient embedment below the shear surface to limit movement of the landslide. And the only area on the site where we're able to do that is in the lower hillside, where the shear surface is sort of within 5 to 7 metres of ground surface. Clearly, to protect the railway, might be more ideal to put them on the upper hillside at the embankment toe, but we simply wouldn't have got sufficient embedment below the shear surface, or probably even got to the shear surface at that position. If you can have the next slide, please. So yeah, another consideration for the sheet pile wall arrangement was that we needed to allow relatively free groundwater flow along the hydraulic gradient. So as you can see in plan view there, we arranged the sheet pile rows in a sort of staggered arrangement so that water would have the ability to flow straight off the site. And go on the next slide, please. So with the benefit of hindsight, can now sort of look back at the monitoring results over the last 12 months and see what influence adverse weather had on the site, and hopefully, although only recently installed, what influence our interim measures have had. So this is again looking at one of the inclinometers installed on the downcess, and we can see obviously a lot of movement February, March 2021, again where we're seeing about 7 mil movement a week, and that slows down to around about, well, less than 1 mil a week right up until November. There are a few rainfall events where movement did increase a little bit, but nothing significant until Storm Arwen hit Morpeth in that late November, and then you can see movement rate picks up again where we're creeping back up towards probably 5 mil a week, and around about you can see what appears to be a huge jump in movement, but that was actually just a very localized effect on this inclinometer in particular, which happened when one of the horizontal drains was being drilled sort of within 5 meters or so of this instrument, and that showed a significant movement in the ground. Yeah, very, very local to this instrument, not picked up in the other inclinometers on site, which was quite reassuring. But then again, as you can see, after that jump in movement, the drains are installed. We've got sheet piles at the toe, and movement since January, February has been back to that sort of 1 mil a week or less, the sort of residual creep, which is quite good to see. And that kind of leads us on to the design of the long-term measures. So if I can have the next slide, please. Various options were considered for long-term design. Now, although the interim measure of reducing pore-water pressures on the slip surfaces was considered to be the most sort of cost-effective method of improving stability, certainly in the short term, given the size of the main failure, the high groundwater levels, the poor condition of the existing slope drainage, and the limited options for outfall of drainage onto what was obviously the river floodplain and a level toe, providing sufficient effective deep drainage across the unstable hillside for long-term stability wasn't really considered a viable option just in isolation. And again, as I mentioned earlier, another requirement for any remedial solutions to allow free flow of groundwater beneath the slope, and that discounts various other options such as a full-length sheet pile wall or a contig pile wall. We also considered some of the more extreme options to improve stability, such as removing the destabilising upper part of the failure by removing the East Coast Mainline embankment and either replacing it with lightweight fill or sitting it on a piled slab or even constructing a viaduct across the site. But obviously all these have been considered and quickly discounted because the obvious disruption to rail operations and rather excessive costs involved. So what we actually settled on as the most effective way to stabilise both the shallow and deep landslides was by installing a couple of rows of space piles across the site to act as a restraining structural element to the hillside. The optimum location for the 4 piles used to stabilise the slope is usually considered to be sort of 1/3 to halfway up the slope, and which is roughly where we've got row 2 shown on that slide. But in this case, considering the size of the primary deep landslide, more than one row of piles was always going to be required, and the location of the piles is going to be controlled by the profile and mechanism of failure of the landslide. If we were to go with just the 1 row, then we'd need to put it close to the toe of the East Coast Mainline embankment, where row 1 shown on this slide, and it need to be where row 1's located. And if we just had I'm losing my thread a little bit. If we just had the 1 row further down the slope, then we'd run the risk of the shallow failure, the shallow secondary failure, just riding up over above the row of piles. Another thing we've got to think about is the translational failure on the lower hillside below row 2, which is obviously unrestrained, and if we get any erosion of the toe or higher pore water pressures in the lower hillside, creating conditions for continued movement, even though we've restrained the main mechanism of the translational failure, which is the loading of the embankment itself at the head of the landslide. We need to put something in place as a sort of secondary stabilisation measure right at the toe of the landslide, and this was provided by the incorporation of the interim sheet piles into the permanent design. And coupled with that, we also allow a bit of reduction in movement by maintaining the slope drainage that we constructed as part of the interim works. It's worth noting though that the long-term solution that we have designed is designed to cope with our critical groundwater level of 50 metres above ordnance datum, just on the basis that it's unrealistic to expect a very long design life for any drainage sort of installed on a landslip. It's going to deteriorate probably faster than the 60 years you'd normally allow for design life for any drainage. We can just have the next slide, please. So yeah, we've gone with the space pile system, and typically the spacing between the piles is on a slope is usually somewhere between 3 and 5 pile diameters. However, spacings in this case are largely a function of the structural capacity of the pile sections, the pile diameter, and to limit lateral deflection. And because we're working on an unstable hillside with difficult access, we're kind of limited to using smaller piling rigs and lifting equipment, simply because bringing in a conventional piling rig to build or sink a sort of 110, 120 diameter pile simply isn't feasible on this site. And because we're using the smaller piling rigs, that limits our pile bore diameter and also the space within the pile to house sufficient reinforcement to accommodate the high bending and shear that are going to be seen by the piles. And just sort of by some early contractor engagement, speaking to the piling contractor, we came to the conclusion that the largest pile bore we're going to be able to achieve on the site was going to be a 750 mil bore. So in order to accommodate the high bending and shear that we're going to see now, our only options for reinforcement was either going to be a circular hollow section steel tubes or universal column reinforcement. And again, buildability came into that, because talking to the contractor, pitching and welding universal columns that close to the railway line is always going to be a problem on an unstable hillside again. So what we've actually ended up going with is the CHS sections, which can be threaded in much shorter sections and generally are easier to construct on site and weld together. With our proposed design comprising 2 twin rows of concrete piles reinforced with CHS steel tube at a 3D spacing, and that's as we can see on the plan there, we have a twin row. The lower plan view shows the twin row immediately at the embankment toe, and then the upper row on the slide there, she shows a sort of staggered twin row with the grey box marking the a sort of exclusion zone that we've got around some high voltage wires, that overhead wires that cross the site at that point. I've probably rattled on long enough about the design now, so it's probably time for me to hand over to Ben, who's going to talk about the actual progress of the construction works on site and where we are now with the sort of procurement of the long-term remedial works.
Yeah, thank you, Nick, and good evening, everyone. So Story Contracting, the company that I work for, are the principal contractor for the Morpeth project, and we mobilised to site on the 18th of October last year, meaning we've been on site for about 19 weeks to date now. During this time, we've imported over 10,000 tonnes of stone in order to prepare our enabling works across the hillside. And you can see on the screen the layout of our site as it currently stands. Access to the site is via the single width tarmac road, as shown in orange, leading into our compound and haul road areas. So everything in purple illustrates the scale of our enabling works that have been needed just to gain access to and onto the hillside for our plant and equipment in order to deliver the interim measures. What the plan does not show you is the topography. You head down a negative gradient along the tarmac road in orange and into a flat arable field where the compound area is located. We've then needed to install the lower hillside haul road and link road against a steep positive gradient up the hillside to the positions of the piling and drilling platforms. You may have noticed the right angle bend between the lower hillside haul road and the link road. This is because we've optimised the route taken across the hillside simply by working with the natural topography to minimise the amount of excavation and backfill that we needed. We recognise at a fairly early stage of the project that the scale of the enabling works and the temporary works would be considerable. So we engaged with our material supply chain in the northeast region in order to identify large and reliable sources of recycled aggregate. The sourcing of the recycled aggregate has minimised our impact on the environment through reducing the need for primary or virgin aggregate, whilst also ensuring the material we used was of sufficient quality for our needs for the temporary works. We took this one step further by sequencing our works so that the piling platform was installed first and allowed our supply chain partner, SPI McGrattan, to install the sheet piles early on in the construction programme. We then reused the aggregate of the piling platform, which was approximately 1,000 tonnes during the construction of the piling platforms, to reduce the amount of total stone that we used on site. The photo to the left of the screen better illustrates the scale of the hillside slope, as well as the scale of the site. With the failure mechanisms at play, as Nick has previously discussed, and with the large items of plant, such as the 55-ton leader rig or the 25-ton drilling rig, working on top of an active earthwork failure, we were acutely aware that our construction works could have a potential to exacerbate the failure and movement in the hillside, which was even more pertinent as the railway was open to traffic throughout the duration of the scheme so far. This meant that we needed a collaborative approach to our temporary works designs, whereby we held regular forums with our key primary stakeholders such as SPI, Keller, Pell Frischmann and Richter Associates. And during these forums, the teams had an opportunity to discuss iterations of the designs, ensuring that all stakeholders were provided an opportunity at regular intervals in order to provide input and feedback on the temporary works designs. This helped ensure that the temporary works designs were suitable for use by our supply chain partners, but also ensured that we considered the impact the temporary works would have on the hillside. The photo to the right of the screen shows the 55-ton leader rig during the installation of the sheet piles. So in total, there were 142 12-metre AZ24 sheet piles that we installed over a 2-week period. And this was completed by the 26th of November, which was just 6 weeks after we initially mobilised to site in mid-October. The photos now on the screen show the drilling rig during the installation of the inclined drainage on the upper row. And we employed the use of a cased lost point drilling methodology. We selected a cased drilling system in order to reduce the likelihood of running sand occurring, which would and could cause localised movement if encountered. So our cased lost point methodology involved drilling a 133mm diameter casing with the lost point drilling head directly into the hillside. And once the casing had achieved the design depth or a reasonable refusal depth, then a smaller 63mm diameter perforated pipe was installed. The photo to the top left-hand corner shows the lost point drilling head. So following the installation of the perforated pipe, the drilling rig extracts the casing, leaving the lost point drill head and the perforated pipe behind. The photo on the right shows the attendant excavator with a manipulator attachment, adding and removing 2-metre length casings from and to the drilling string. Our work to install the 31 number incline drain positions commenced on the 4th of January. And installation was completed by the 3rd of February. And the lengths of the drains vary from 40 metres up to 50 metres. But in total, we've drilled over 1 kilometre's worth of drainage into the hillside in just a 4-week period. As the project looks ahead to the delivery of the long-term solution, we have already procured over 4,000 linear metres of steel tube reinforcement, which have been identified by our piling supply chain partner, Keller. The tube we have procured is existing CHS stock that's been repurposed from the offshore pipeline industry. And so through the repurposing of this existing stock, of this existing steel, we've been able to reduce our costs to the client. We've been able to reduce our material lead time risk and also reduce our carbon footprint. On the approach to the site, our vehicles need to navigate a level crossing, which is a sharp left-hand bend in the road that will prevent us from delivering the tube in single lengths. So this means that we need to take the existing stock that's currently based in Thirsk, and we will chop it up and we will thread it. You can see on the bottom left-hand photograph of the screen, that's the threading in process up in Scotland. The team will then screw together sections of the steel and weld them once they're on site before installation into the piles. And this follows a similar methodology to one that we'd successfully employed on a previous scheme at Hessel near Hull, which was delivered by Story and Keller on behalf of Network Rail. Our piles at Morpeth will be installed using a continuous flight auger CFA methodology by the piling partner Keller's. The image to the right of the screen highlights the CFA process, whereby the specialist piling rig will auger down to the required depth, and as it retracts and concrete is pumped into the bore through the hollow stem of the auger, the steel reinforcement is then plunged into the freshly cast high slump concrete by a crawler crane. We anticipate we may need about 2,000 cubic concrete. So our proposed concrete mix will contain 70% cement replacement materials to help us deliver a more sustainable intervention in combination with a repurposed steel reinforcement and the use of recycled aggregates for our temporary works. We expect the construction programme for the long-term solution to be approximately 35 weeks, with piling due to commence from May, meaning that upon conclusion, the delivery for both the interim and the long-term interventions, we will have had a presence on site for well over a year in order to protect the railway from the large landslide at Morpeth. So this concludes our presentation on large landslides, and so thank you for your attendance, and we'd like to spend the next 10 to 15 minutes answering a few questions.
So yes, we've had very many excellent questions from our audience. I am going to go through the questions by how many likes they've received. So to begin with, we have Phil Wilson, FICE. Has Network Rail established any correlation between climate change and the frequency of landslips? What is the strategic and tactical response?
I'll take that one, if that's okay. Well, there's obviously a connection between landslips and high rainfall, high groundwater, in terms of climate change. So the connection there is that you get more frequent high rainfall and storm events and flooding events, and so we will see more landslips. In parallel with that, we are doing more work. So there's a lot of information, a lot of data out there, and knowing exactly which landslip was caused by, for example, climate change is difficult to see. You need to look at it as a kind of population level thing. So, and in terms of so day to day, we do a lot of the stuff I described earlier. We have programs of, you know, assessment to try and understand our earthworks. We have programs of maintenance to try and prevent things like blocked drains, you know, causing an earthwork to deteriorate. And then we also have a program of monitoring that will help us identify when slopes have failed and stop drains, and programs of renewal. So that's kind of those are the things we're doing to try and prevent landslips. I'm not sure if I fully answered that question, but
okay.
Yeah.
The next question by William Powry. I seem to remember when I was working for British Rail Eastern Region in the early 1980s, there was a program of filling in redundant culverts to save money on maintenance. Is this unwelcome harvest of this short-sighted policy now being reaped, and are there other instances now causing problems?
Yeah, so I don't know that particular culvert at Morpeth. I suspect wasn't part of that, fitting in these supposed redundant culverts. That it has caused problems, and we do occasionally find culverts again. We've got bigger culverts which are managed by the structures team. I think those are over 450 millimeters diameter, and then there's more the drainage pipes and smaller under-track crossings or whatever. It can cause problems, and we try and fix it when we do come across them. Or yeah,
I think if I can interrupt by the culvert on the Morpeth site, there is a culvert issuing from beneath the embankment. I think it's kind of always been an assumption that at some stage was a UTX leading from the sort of infilled area of the container yard, but if you actually look at the alignment of the culvert, I suspect rather than a UTX, it was just a sort of cut and cover drain placed as they were building the embankment to pick up probably a spring or a seepage on the embankment side, on the hillside rather, before the embankment was constructed, and rather than being infilled at any stage, it's more likely that it's just collapsed because it's kind of immediately in the shear surface of the secondary landslip that we identified on site. So that probably broke the back of it some time ago. And when the berm was added in 2016, the culvert was just extended, and even at that time there was no water actually coming out of it any more than a little trickle, and that remains the case today. So yeah, it probably is linked in part to the failure in that, yeah, disturbance of it has stopped its function as a drain, but there's certainly no evidence that it was ever intentionally backfilled.
Hey, that's interesting. I'd managed to miss that one.
Right.
The next question from Chris Preston. Has remote condition monitoring been considered or used at Morpeth to allow better understanding of the landslip?
There is various kinds of instruments being used on the track. Nick, do you want to?
Yeah, I mean, we've got sort of remote sensing equipment. We have slope mates, sort of data logged inclinometers, if you like, which give us day-to-day readings of movement on the ground, which we can obviously go to the website and check every day to see if movement's picked up or if there's any movement on a particular part of the site. What else have we got? We did have the smart, well, we do have the smart track system on the tracks themselves to look at twist and crossfall on one of the roads. We've had issues with that because I think every time the tracks are re-tamped, everything has to go out. Everything has to be cleaned to get it up and working again. But that has been a very useful system for picking up the track deformation in between, you know, the amber trolley runs that we do a couple of times a week, just to keep on top of any movement in the twist and crossfall. But yeah, everything else is generally manually monitored, inclinometers and extensometers and piezometers that we go out and monitor twice a week.
So Nick, we're also planning to install some SMAs into the piles.
That's right, yeah.
Connecting to the RCM network of DVDAG and Dayton.
Yeah, that's right. Just to measure performance of the piles when they're installed, we'll have a series of SMAs that, yeah, as Ben said, will be remotely monitored so that we can, yeah, get minute by minute records of any movement or deflection of the piles.
May I ask what does SMA stand for?
Slope mate array. Essentially just an array of sensors installed within the borehole that pick up movement of the ground at, well, whatever spacing you're prepared to pay for the sensors to be installed at. So again, it just gives you a sort of live feed of deflection of the ground and at what depth that deflection's occurring.
Okay, the next question is the geotech team looking at using SatSense software to monitor when and where potential landslips may occur?
So it's we've looked at it, and I don't think it is right. This is my memory of having looked at it before. I don't think it's right for the kind of small scale landslips that we get in our earthworks, which are often quite heavily vegetated, and they'll have very small, you know, they'll be hard to pick up in that using that kind of technology. I think there is potential use for it. Looking at, so I'm just looking at some notes I made on SatSense sometime last year. So you know, it might be useful for looking at things like changes in neighbouring land, potentially what kind of settlements you might get from historic mine workings or compressible ground such as peat. Or there's also location of rebound, where the groundwater levels have changes following cessation of mining. So you might have some movement there. So there is some potential in there, but I don't think it's something that I can see being able to be used very quickly in terms of our kind of landslip, our typical landslides.
Okay. Next question was, did the perforated pipe drains work? Was groundwater found to have flown from these?
Yes, yeah. So we've actually started to see some of the upper row drainage flowing at the moment. We weren't strictly flooded as soon as we installed the perforated pipes. It's been fairly modest flows that come out of them, but we have seen them working.
And it's also notable that certainly in my presentation I talked about the characteristic groundwater level of 48 metres above ordnance datum, which is what we've sort of based a lot of the design on. But it may not seem like it at the moment, but we have had quite a dry 12 months. So, you know, groundwater levels have actually not got back up to that 48 metres. So we've got the two rows of drains, and the lower row of drains are pulling water out the slope. The upper row of drains are round about, I think they're 46, 47 metres ALD. So just because of where groundwater is at the moment, they're not pulling a huge amount out. But yeah, considering the weather we've had over the last few weeks, that might all start to change soon.
Okay, next question, which would be, on what basis was the decision taken to recruit internal NR earthwork examination team rather than using consultant engineers?
Take that one. So it's been something I've wanted to do for a very long time. I've always felt that our examiners who are out on site looking at our earthworks, they obviously see it, you know, day after day, year after year. They see what these earthworks look like, and the way it had worked was they were kind of external, and there was just this kind of gap that I could see between what they saw on site and the actions we were taking in our team. And so the opportunity arose within this past kind of year and a half to put a proposal forward to bring the examiners in-house to try and, from my point of view, and we'll see how it goes over the coming couple of years, I guess, is to shorten that gap between them seeing issues on site and us including that information in our asset management, our decision making around what kind of work is needed, what kind of assessment is needed, etc. So that was the idea. I hope I've answered your question there. The basis was I thought it would help our team manage the assets better.
Excellent. Then on to I think we have until 10 more minutes until 7 o'clock. I'll basically go through the list as well, and I've got a few more to go through. So the desk study identify ancient landslips. What were the anticipated ground conditions?
Yeah, I'll take that one, I guess. Yeah, the anticipated ground conditions. Obviously, we go to the BGS maps, and again, ground conditions in this area are sort of fairly well understood. As I said, you tend to, in a lot of glacial soils in this part of the northeast of England, you have this tripartite system of a glacial till, more granular glacial till, sand and gravel, and then a laminated clay, and then back into a glacial till, sand and gravel, laminated clay again. And yeah, that's exactly what we found. And in terms of the ancient landslips, that is a good question, because again, that came up in the desk study, and looking at the geological memoirs and the maps of the area, it is noted that a lot of these glacial soils have actually failed in the past, failed during the glacial periods or shortly after, and quite often may be at residual strength or sat round about unity in terms of the factor of safety and on stability, such that any change in loading conditions on the slope, such as someone coming along and building a railway embankment on top of it, is going to induce further failure. Or say if the groundwater conditions change, or if the track's constantly reballasted because we're getting track faults because of the movement, all this induces further failure. And it may be that what we're seeing at Morpeth is a reactivation of a glacial or interglacial landslip, or it may be a new one, or well, it's certainly not new, but more a 19th, 20th century landslip, or it could be that it's as you say, a sort of glacial landslip that's just sort of been reactivated by construction of the railway, and then more recently increased groundwater levels. It's impossible to say really, but it is something that's noted for these ground conditions, that yeah, there are lots of relic landslips around, and it's entirely possible that this is just a reactivation of one of those.
Now, I'm mindful of that we have 3 other questions that have been unpublished, and that 2 questions from Cameron and Paul have been answered by Claire. So what I'm going to do is I'm now going to publish the 3 questions, and I'm going to ask them on the chat. So I've just published them. So the question is, question to contractor: have you started looking into trialing more sustainable power source of fuel in the rigs and site plants? Is this feasible?
Yeah, so for this site, as we move into the summer months, we'll be looking at using what they call like a solar tainer, which is essentially a container that's spliced in half with some solar panels shoved on the side in order to reduce our fuel use to power the compound.
Okay, and our next questions by Matthew Roberts. Fantastic joint presentation, taking us through the full project cycle. Thank you. What's the estimated cost, and how to NR budget for what might be short notice projects?
Yeah, I'll take that one. So the cost at the moment is in the region of £13 million, and that includes costs that we've been spending on the permanent way interventions to keep the track going, and that doesn't include the overhead line works. So so that's the kind of budget you're talking about, taking into account that my budget for the East Coast kind of renewals budget each year would be in the region of kind of maybe £5 to £10 million each year. So it's, you know, it's a really big project for us. Our only other bigger one is the one at Brownie Curve, which is a whole other story, and but that one's been, you know, years in the planning. So in this particular case, it's, you know, 12 months ago we were thinking, oh, we've got to build this. Where are we going to find the money? You know we have to do it. So within my team, we actually deferred one of our projects. We felt we could manage the risk from that. We've deferred that to CP7, and that was a roughly £5 million project. So part of the 12 million has come, or 13 million has come from our budget, and then the route has found money elsewhere. So the remainder has been kind of added in. So it's quite tricky when something like this happens, because you want to be, you know, you want to have a good work bank, you want to know what you're doing in advance so that you can, you know, do it efficiently and all of that. And then something like this comes, and it does throw things off. The intention is that we will get fewer and fewer of these as we understand our earthworks and our adjacent hillsides better over the coming years, and that we will not be surprised by these. Hopefully that answered your question.
Okay, so I'm thinking we have one last question left to go through, and so that's I want to choose one last question in terms of will the switch to Great British Rail enhance or impede railway maintenance?
Or if I have any influence, it will improve it. I guess the intention will be overall that this will point us in a better direction, and that we will end up having a better railway out of this. So part of that is doing the right maintenance at the right time and knowing what you need to do. So I will influence it as best I can, as I'm sure will everybody else involved.
Okay, thank you very much, everyone, for a fantastic presentation, and thank you everyone for attending. And I hope you have had you enjoyed it. We aim to have this published and put onto YouTube in the coming weeks. And what I have done as well is I have taken notes and slides, and I have recorded all the questions. I will be uploading this information onto our members area of RCEA, and you will be able to see the notes and the slides taken from this project. Thank you very much, and good evening.
Thank you, everyone.